Hey, today we're going to talk about nuclear chemistry, and nuclear chemistry, like it sounds, just has to do with the nucleus. Top number refers to the mass of a particle. The bottom number, as we've learned, refers to the number of protons. However, in nuclear chemistry, we're getting a little bit more specific and a little bit more precise, so this number really refers to the charge of the nuclear particle. Since carbon only has protons and neutrons in its nucleus, this refers, the charge is a +6, which is the same thing as the protons. So when we're notating atoms, this is the number of protons. When we're notating nuclear particles, it is actually the charge of it. I want to determine which one of these is going to be stable and which one is going to be unstable. So if I look here, carbon-12 has 6 neutrons, because 12 minus 6 equals 6. Carbon-14 has 8 neutrons. Since carbon-14 is off balance, carbon-14 is considered to be an unstable nuclide. Now what does that mean? An unstable nuclide is something that will spontaneously decay, which means it's going to shoot particles out from it. And what are the particles we're talking about? Well, if you look at this table right here, we have a bunch of different particles. I'm going to talk about three in particular. We have the first one, which is an alpha particle. See how I drew that? You can also draw it. These are the same thing, different ways of writing it. An alpha particle is simply the nucleus of a helium atom. Helium atoms have 2 protons, 2 neutrons. That's in the nucleus. Then they got the electrons floating around, but this is just the nucleus. So you could write it either way. In fact, the alpha particle is the particle that Ernest Rutherford was shooting at the gold foil. Remember when the particles bounced back at him? Those are alpha particles. Another example of something is what is called a beta particle. A beta particle has no mass and a charge of -1. They also write it like this. That's because a beta particle is basically just an electron. Now we have a positron, which has no mass and a charge of +1, and can also be written like this. Forget it, let's do one more. We also have, and they only ask one question on this, a gamma particle has no mass and no charge. Since it has no mass, no charge, it's basically just pure energy, and it will shoot very far, very fast. It has the greatest penetrating power, which means any substance that is near it will be penetrated by it. The gamma particles are very damaging to humans, very damaging to the environment. When gamma particles are emitted, they're very common in space. They're not as common here, but if you get hit with gamma particles, it's not a good thing. If you survive, your DNA will be heavily mutated and you'll probably just die of cancer eventually. Okay? So, what you're going to do is you're going to try to figure out stable or unstable, and then you're going to figure out which type of nuclide we're dealing with and which type of subatomic nuclear particle we're dealing with. So these are nuclear particles. Okay, we have 2 types of nuclear decay. Basically, any type of decay is when it changes from one to the other and it's giving off particles or being bombarded with particles and still changing into something else. We call this process transmutation. Transmutation because it's changing into something else. Now I'm going to look at table N for something like a natural transmutation. Natural transmutation just has one substance or one isotope on the left side of the arrow. And that's going to change into something else. An example like this, when you have 2 different substances, that's going to be artificial transmutation. I'm taking a beryllium atom and I'm bombarding it with alpha particles. I'm going to come to this one in a second. This first one, I have carbon-14. So I'm going to look on table N, and I'm going to notice that carbon-14 is the second one. Carbon-14 undergoes beta decay. So what happens is carbon-14 is going to change it's going to get rid of a beta particle. Remember, we draw our beta like this. If you can't draw it properly, make it an E. And then it's going to change into something else. Now, how do we figure that out? We have to treat this like math. This arrow is treated as an equal sign. So you have an equals on top and an equals on the bottom. 14 equals, 14 equals 0 plus x. What is x? Well, 14 equals 0 plus 14. Now this next one, we have 6 equals, and I'm going to write this one out. 6 equals negative 1 plus x. What I'm going to do is add 1 to both sides, cancel that out. 6 plus 1 equals 7. So, in our natural transmutation of carbon-14, in other words, the decay of carbon-14, I'm going to get it changing into a new element. I look in the periodic table, find out which one matches, which one has the atomic number of 7, and I notice that is nitrogen. Okay? Now, in artificial transmutation, all you'll ever have to do, one thing you'll have to do is identify which one is which. And like I said, if you only have one isotope on the left, it is natural. If you have an isotope plus a nuclear particle, it is artificial transmutation. But what they're going to do is they're going to give you something like, and you have to fill in the rest. So this is what happens when you bombard alpha particles with beryllium. So let's figure out what we're left with. So again, we're treating this like a math problem. 9 plus 4 is 13. So 13 equals 1 plus x. 13 equals 1 plus 12. This next one is a little bit easier. 4 plus 2 equals 0 plus x. Again, 4 plus 2 equals 0 plus 6. Now I don't need to look too far to find out that when the number on the bottom is 6, that equals the number of protons in an atom. That is carbon. So this, again, artificial transmutation. This one at the top is natural transmutation. One more example. Now you guys have all heard of uranium. And uranium is very common in nuclear reactions. And we'll talk more about the nuclear reactions in a video upcoming. However, this example right here, I'm going to look up uranium-238. Uranium-238 is on the very bottom. It undergoes alpha decay. Now, when you undergo alpha decay, let's fix that a little bit. If you notice, alpha kind of looks like a fancy letter A. It almost looks like a fish, but it's not quite like a fish. It's hard to draw. If you can't draw it, put an HE. Alpha decay plus something else. So again, let's treat this as a math problem. 238 equals 4 plus x. In other words, 234 plus 4 is 238. 92 equals 2 plus x, or 92 equals 2 plus 90. I'm going to look it up on the periodic table. Right here is atomic number 90. That becomes thorium, or TH. Now the only time you really need to watch out is when you have beta decay. Because if you look, it goes from 6, -1 to 7. So if you have beta decay, this number is going to increase. And that's just because anytime you throw a negative in there, it messes things up. Keep that in mind. Look at the practice problems. Good luck.